Thank you very much. I'm very sorry for being late. So the title of my talk today is Higgs Coulomb correspondence and wall crossing for abelian gauge linear sigma models. This is based on joint work with my colleague Konstantin Alyashkin. It's dedicated to the memory of Professor Bunsi Kim. We rely a lot on Professor Kim's work. So first of all, I want to say that the Higgs branch and Coulomb branch in this talk is not the same as in the previous talk. So here is the plan. The first part, thanks to David. So I will briefly review gauge linear sigma models in the set of David's lectures, and then by Higgs branch, we mean like virtual counts of Landau-Ginzburg quasi-maps. And then I will introduce Landau-Ginzburg loops and I functions in the GLSM setting. And we will define central charge where curly B is a B-type brane, a matrix factorization or a coherent sheaf, and bracket B is so this only depends on the K-series class. And the third part, the Coulomb range, we will introduce hemisphere partition function following Romão. And so by Higgs Coulomb correspondence, we mean the hemisphere partition function in the Coulomb branch is related to the central charge in the Higgs branch. And finally, we will discuss GIT stability wall crossing. So here the setup, so recall from David's talk that the input data of gauge linear sigma model is 5-tuple V gamma chi W nu, where V is a complex vector space of certain dimension. Gamma acts linearly on V, and chi is a character of gamma. So we call the target C star omega and the kernel G, the gauge group. The superpotential is a polynomial on V, which is invariant under the gauge group. And so when for elements in gamma, so it satisfies this relation. Also, nu is a Q character of gamma. And so in this talk, so in the David's talk, theta is the restriction of nu to G. So in this talk, it will be zeta. So it's a rational character of the gauge group. So also we will have like this C star is another subgroup of GLV. It's isomorphic to C star, commute with the action of G, and together they generate gamma, and their intersection is some finite cyclic group. And it's known as the R symmetries. So we have the same requirement as in David's talk. So the notation is we call the GIT quotient stack curly X sub zeta. And the superpotential W descends to this quotient. It's called W sub zeta. And the C, so now the C, oh, so there's a typo. This should be C star R. Yeah, so this should be C star omega. So in most of this talk, we will consider an abelian gauge linear sigma model G acting on V. So G is just not only abelian, but it's actually a torus of certain dimension K. It acts on V by G characters D1 up to D capital M. And the C star R acts on V by weights C1 to Cn, which are integers. By the physics convention, we call 2Ci over R little qi. So CIR is the action. So C star omega doesn't really act on V. It acts on the quotient. So we have fractional weights. Okay, so in the abelian case, this GIT quotient is a tori Deligne-Mumford stack in the sense of Bryce of Chen and Smith. It's a smooth tori Deligne-Mumford stack. So it can also be presented as a symplectic quotient. So here, GR is the maxima torus, and mu is the moment map of the Hamiltonian action of this maxima torus. So the image of the target of moment map is the dual of the real Lie algebra. So in this talk, we will also want to allow zeta to be a real character. And the space of stability condition is an R-dimensional real vector space. So the chambers are in one-to-one correspondence with the top dimensional cone in the secondary fan. Okay, so this is so let me go through this example again. So example of this abelian gauge linear sigma model, let V be C6 with coordinate x1 to x5 and P. Gauge could be C star and gauge group X by weights 1, 1, 1, 1, 1 minus 5 and C star R, which is equal to C star omega in this case, just X1. And this is the superpotential is P times the Fermat quintic polynomial, which is invariant under the action of G and C star R X by weight 1. In the Flavial case, the stability condition tells us Xi cannot be all 0. So we get, so GIT quotient is KP4. And the critical locus of superpotential is the quintic threefold in the zero section P4. And in this case, the GLSM invariants are Gromov-Witten invariants of the quintic Flavial threefold. In the Landau-Ginzburg case, correspond to negative zeta. P cannot be 0. We get this orbifold. The critical point, the critical locus is supported at the origin. We have a fat point. So as we know, in the when zeta is negative, Landau-Ginzburg phase, the GLSM invariants are FJR invariants of the Fermat quintic polynomial. So Kyoto and Ran proved the Landau-Ginzburg-Flavial correspondence for quintic threefold. So Landau-Ginzburg-Flavial correspondence for quintic threefolds relates Gromov-Witten invariance of the quintic threefold and FJR invariance of the Fermat quintic polynomial. I think their proof, so they prove a version which is genus 0. Their proof can be summarized into 2 steps: epsilon wall crossing and zeta wall crossing. So thanks to Jung 6 talks, we know epsilon wall crossing. So as we know, like so by epsilon wall crossing, we meet Giventhal-Stiles mirror theorem, which is a relationship which says J function is related to I function by mirror transform. In the Flavial case, this is first proved by Giventhal and Liang Yao, and Xiaoken, Fontanina, and Kim interpret this as epsilon wall crossing, and they have stronger results. And in the Landau-Ginzburg phase, so Gilda and Ran actually prove Giventhal-Style mirror theorem also is of the form J is related to I under mirror map. Again, like I is explicit hypergeometric series, and J is a generating function. It's defined in terms of genus 0 FJRW invariance. And later Rose and Wan also give proof in terms of as epsilon wall crossing. So both I plus in both phases, IJ are functions of one variable and takes value in this complex symplectic space. Also here H0, H2, H4, and H6 are like the graded pieces of the state space. And so the second step, zeta wall crossing, is to relate the I in the Calabi-Yau phase and I in the Landau-Ginzburg phase. And they are related by analytic continuation and complex linear symplectic isomorphism of these two complex symplectic spaces. So now, thanks to Farewell and Kim, we have definition of GLSM invariance for general GLSM and in all phases. So it's natural to ask, so the generalization of Landau-Ginzburg Calabi-Yau correspondence can also be proved by proving epsilon wall crossing and zeta wall crossing. So let's first recall what is done for orbifold quasi-map theory, which can be viewed as a mathematical theory of gauge linear sigma model without superpotential. So the input data is just VG and zeta, and it counts epsilon stable maps to this GIT quotient. So Chung, Xiaochen, Fontanelli, and Kim, so they prove epsilon wall crossing, and which implies given-Tau style mirror theorem. And in particular, when G is abelian, so this implies the mirror theorem for smooth tori Deligne-Mumford stacks by Cordy, Irtani, and Zeng. So there are like, so also Chilcom, Fontaine, and Kim, they prove like higher genus epsilon wall crossing when when the target has a torus action with isolated fixed point and also complete intersections in projective spaces and so on. So as Jung-Seok mentioned in his talk, so Yang-Zhou proved the epsilon wall crossing in orbifold quasi-map theory in all genera in full generality. So in all the target like for which this theory is defined. So I think, yeah, so it is expected that Yang-Zhou's proof, yeah, this is very difficult and it is expected. Actually, Yang-Zhou's proof should be generalizable to GLSMs. At least, so this is what Yang-Zhou told me that, yeah, I think he will be one of the most capable mathematicians to prove this. So, and in particular, if this is proof, then this will, at genus 0, it will imply given-Tau style mirror theorem for general GLSMs in all phases. And I know Mark Shoemaker is also like thinking about this. And indeed, this has already been proved by some GLSM. For example, yeah, for example, like Kleder, Jandal, and Ram prove higher genus epsilon wall crossing in the gauge linear sigma model, which is associated to complete intersections in weighted projective spaces. Yeah, so today I'll like address maybe in my work with Aliashkin, we address the so we want to discuss the I function and zeta wall crossing for abelian GLSMs. So for Higgs branch, so these are the references, and also David gave 2 talks on this. So that I don't have to go through this part, the general theory. So the only thing I want to like mention is that we are in the abelian case, so there's a lot of simplification. So recall that a Landau-Ginzburg map is consists of 4 things. So an orbit curve, a gamma bundle, kappa and U. So it's summarizing this So in the left diagram, so basically this Landau-Ginzburg map, if we ignore the stability condition, it's gives a map to the V quotient by gamma, and so then it has there's a map from V quotient by gamma to P gamma, and that's the principal P bundle. And recall that there's a character from gamma to C star omega, which determines a line bundle, and we require that line bundle is the log canonical. And the upper half of the left diagram, as you have seen in previous talks, so it is the same as a principal gamma bundle to get P together with a gamma equivariant map F. And also we know that this is the same as saying that it's a section of the vector bundle associated to V. But now we are in the Abelian case, this can be simplified because so our gamma actually acts on this so this should be capital N, so it's C capital N, so it's direct sum of capital N line bundles, and the section is just capital N sections of this capital N line bundles. And in our case, G is a k-dimensional torus, gamma is k plus 1-dimensional torus. So the degree of I think there's some so this is not quite okay, so I think there's some typos, but I just want to say that the degree of, so rationally the degree of P can be split into the degree of a G bundle and degree of C star omega bundle, and degree of the C star omega bundle is fixed to 2G minus 2 plus L. So recall that in June 6th talk, in orbifold quasi-map theory, and more generally orbifold quasi-map theory, I function is obtained by C star localization on quasi-map graph spaces, noted by GQD, so where D is some effective class. So there's also, it can also be, so there's a particular component of the fixed locus. So C star in this talk, so the C star acting on the P1 will be called C star sub Q. So the novical variable from now on will be called Y instead of Q. So this is very similar to the notation in June 6th talk. So F0D is a component, and so the I function, there are some prefactors, so it's defined by push forward of the virtual fundamental class of F0 divided by the C star equivariant Euler class of the virtual normal bundle. But there's also a stacky loop space, and in the toric manifold case, it's correspond to the toric map space introduced by given talk. So for the stacky, so there's a fixed locus FD, which is isomorphic to F0D, and also if we can also use the stacky loop space to do this localization, we will get the same result. This is because these two spaces are the same along FD. So what we will do is we will introduce the Landau-Ginzburg loop spaces, which are analogs of the stacky loop spaces, and then we will define our I function using stacky loop spaces. And actually, since we are in abelian case, this is really easy. So recall that because of the orbital structure, so the domain is a PA1 with only possibly one orbital point at infinity 1, 0. So A is a positive number. And so it will be, so A can vary, so it will be convenient to reintroduce this notation. So we didn't, so if A is a positive integer and M is an integer, so we define P1 O M over A to be this group. So this only depends on the ratio M over A. So now suppose that we have an effective class, and so we can pair, so this is a rational co-character of G, and it can be paired with the G character Di. Recall that Di is the character for the G action on the I coordinate, and there's a shifting coming from the C star omega action. Yeah, so that's very easy. So when there's so this is very similar to the in orbital quasi-map theory. So there's no QI. So we define degree for this effective class. We define degree V Landau-Ginzburg loop space. So the G acts on the I's part just by the character Di. Yeah, so this LG loop space is actually a smooth smooth toric Deligne-Mumford stack, and the obstruction bundle is a smooth toric bundle. And now, right now, there's no superpotential yet. So we have so this T tilde is acts diagonally on is the diagonal torus of the vector space V. So it acts on the stack, acts on the Landau-Ginzburg loop space, and the obstruction bundle is a T star C Q star equivariant, and XD sigma is so here so there's an open substack where the evaluation at 1, 0 is defined. So so meaning that it goes actually in the stable locus. And actually the evaluation map takes value in the inertia stack. And then so now suppose the inertia stack is a disjoint union of connected component. We label it by B. And so which component is actually determined by this effective class D. And now, so as before, we actually consider the C star Q fixed point and call FD C. And actually, the evaluation map restricted to this becomes an embedding of, so this is actually closed toric substack. And so let M virtual D be the virtual normal bundle. And it has a natural extension to the ambient X. So let's see. Oh, so now here, this is like really nice case. So we know that, but to define the virtual fundamental class in this GLSM setting, we should follow Farrell and Kim's construction. So this is like specialized, the very technical and difficult construction to a very, very easy case as follows. So we fix So we fixed D and let V to be the connected component determined by this effective class. And that W zeta V denote the restriction of the superpotential to this connected component. And the pullback of this, so the pullback under the evaluation map of the superpotential will be 0. So now, actually, this substack actually before the quotient is just a subvector space. So it is cut out. So we can suppose let x1 to xm plus be the coordinate on v plus and p1 to bm minus be the coordinates on v minus. So then this is embedded as a zero locus of this regular section, which is just given by p1 to bm minus. And I'm sorry. So this is not so this is not updating, so I need to stop for a moment, sorry. Okay, yes. So yes, so we can so now we know that to follow the construction of Farrell and Kim, so although this F is already smooth, but we need to we still need to extend it, embed it into a larger U, and such that essentially we need the evaluation map to be surjective. So in this case, we can just take U to be X, to be this component of inertia stack. And then, so basically the extended evaluation map will just be the identity map from the X CV to itself. And then since this superpotential restrict to 0, so we can write it in this form, where xk, there's some ambiguity in choosing wk, but there exists a choice. And when restrict to f, they are just partial derivative of the superpotential with respect to pk. Now, so we can just let alpha to be this. This is a cosection, and following Farrell and Kim, so the pairing with this sectional cosection gives the factorization of the superpotential. So we take this kazoo factorization, and this kazoo factorization is actually a regular kazoo factorization of X with the negative superpotential on this connected component of the inertia stack. And so we define, so actually this, and moreover, when the superpotential is 0, which is true, see, inertia stack, so V is called narrow if this inertia stack component is compact, and in that case, W is 0, and in that case, the cosecant will be 0, and we get Kazoo fact. We just get the Kazoo complex. So, so we actually get the virtual structure sheaf in the definitional quantum K-series. Then, so this Kazoo, so the virtual structure sheaf is a categorization of the virtual Baron-Fantakis virtual fundamental class, and this Faber-Kim's virtual factorization is the categorification of virtual fundamental class. But actually, I think they first construct this categorical version, and this can be used to define K-theoretic GLSM invariance. So to decategorify it, so we take the Todd and the localized Chern character. Localized Chern character of this regular Kazoo complex. Sorry. Yeah, so then now we also, so this is, so we also define, so we also want to define the following. So so this will define the GLSM I function. So this F is already an element in the twisted, in the hypercohomology twisted de Rham complex. And and recall that this this N tilde is the natural extension of the virtual normal bundle. So if we follow the recipe, so this is the definition of GLSM I function. And also, we also, because this is a regular, in this case, the virtual factorization is a regular matrix factorization. It can be thought as deformation for the case where the superpotential is 0. So we also want to consider the case where the superpotential is 0. So we don't actually use the superpotential, and then so we use so when superpotential is 0, actually we can have larger torus action. Recall that this T tilde is the diagonal torus acting on V. So we define T tilde equivalent I function. So now we use C star Q times T tilde equivalent virtual class. So having defined the I function, so now we are going to use the I functions to define central charges. So given matrix factorization of W, and take the K-series class, and we take the the central charge of this matrix factorization is defined by pairing the I function, like it's the hypercohomology, an element in the hypercohomology twisted de Rham complex by negative the superpotential by so this by the Chern pair it by some gamma hat, which is a generalization of or analog Iritanis gamma class. And thanks to the work of Cho Kim and Schroeder, we know how to define the Chern character of matrix factorization. So this is actually the Chern character which appears in the Riemann-Roch of Stucky matrix factorization. So it has contribution from twisted sectors. And so now we use the T-equivariant central charge to T-equivariant I function to define T-equivariant central charge. So now in this setup, B-brane is actually a T-equivariant cohomology class, and so we take the K-series class and just take the T-equivariant chain character. Again, will have components from all the inertia stack, and we define it similarly. The advantage of this T-equivariant version is actually we can compute it by torus localization. And in many cases, actually, they are equal. For example, and then in that case, one can actually show that GLSM central charge can be obtained as non-equivalent limit of the T-tilde equivalent central charge. So the next thing is, this is some formal power series in numerical variables. So in this T-tilde equivalent version, it actually has some Moulin-Barn integral representation, which allows one to do analytic continuation. So this is the Coulomb range. So we consider abelian GLSM with the additional condition that it is Calabi-Yau. Oh, let's. Okay, sorry. So now in this case, we are going to complexify the Kähler class. So the real part is the stability parameter, and we also have the imaginary part, which is the B field. So here LC, so this is a notation of the dual of the Lie algebra of the gauge group G. So we consider some. So in this page, M plus kappa is capital N is the dimension of V. So given T equivariant K-series class on the quotient by G, we define this hemisphere partition function as follows. So here, its integral is over the Lie algebra of the gauge group. So it's Cm plus kappa, and the integral. So the gamma. So the integral, the gamma. We have product gamma function, determined by the weights of the gauge group action. And also for a T-tilde equivalent K-series class, so we take the chain character, and that is the formula. And the proposition is actually there exists an open subset there. So for a given T, which is a G character, this is a line bundle. And we on the stack V quotient by G. So there's an open subset U such that, sorry, I'm still not sure about that. So there's an open subset such that this hemisphere partition function for LT is converges. So there's no restriction on the real part. So for the imaginary part, there's open subset depending on T and the B field. Okay, so this is so now, okay, so yeah, so I think I'm running out of time. So suppose that C is the phase of GLSM. So C is a chamber of the stability condition. So it's yeah, so it's a cone, it's the open cone in the it's the top dimensional cone in the secondary fan. So then then the idea is that this integral has in this opens. So when the stability condition zeta is in this open subset associated to this cone, then this has a power series expansion, and this is explicit. And what happens is then we can look at this and compare with the T tilde equivariant central charge we computed by localization, and see that they are related by a simple change of variable. And this is actually expected. And so the proof is by careful manipulation. So basically we start the integral at the beginning is shifted in purely imaginary contour. So one needs to deform it and show that at each stage the integral and series converges. Oh, so finally the wall crossing. So this so I should mention that this has already been done for abelian gauge linear sigma model without superpotential. So in toric-Calabi-Yau non-equivalent case is by Borisov and Hoja, and for so for Coase, Iritani, and Zhang, they actually do the Kreppen transformation for toric Deligne-Mumford stack and toric complete intersection. In particular, they don't need they just require it's a Kreppen. They just require there are two toric Deligne-Mumford stacks related by Kreppen transformation given from cross one wall. And so suppose we are in this setup, and but in the GLSM setting. And so yeah, so actually this notation, yeah, there's a lot of notation, but I'll just tell you the idea. Basically, you get two chambers in the stability condition and then intersect at some wall. So this is in the dual of the real algebra. So it's so the wall is given by perpendicular to some primitive element in the co-character lattice. And then, so if T satisfies this great restriction rule, so this great restriction rule, recall that because of the Calabi-Yau condition, the sum of all di's is 0. And then we take this eta, so which is like pairs positively with edge and pairs negatively with edge. So this is eta. So if we take T, which is in this such that it satisfies this property. So this only cares about like B plus T, the pairing with this edge, which defines the wall. Then we have this so-called wall hemisphere partition function. So it has two parts. So the second part basically corresponds to like the fixed point which are in like both, which appears on both sides of the wall. And then for the essential part, it's an explicit series. So the second part, you just get power series, which will converges in both phases. And the first part, so it's explicit series of integral, and actually, so explicitly of integral, and actually one can evaluate the compact, one can evaluate the k+1 dimension integral, and we are left with a one-dimensional integral. And the analytic continuation is by deforming this one-dimensional contour. So if we look at this great restraint rule, we see that it coincides exactly the great restraint rule in the literature, which is defined in which has been established in much greater generality. So this was predicted by Hurwitz, Horry, Page, and it is so codes you so we have so Ballard, Favreau, Kozakov, Halpin, Leistener has proved like much more general great restraint rule. And in the Torrey case, using their result, Coase, Iritani, Jiang, and Siegel prove that the great restraint rule is equivalent to the Fourier-Mukai transformation. So, so the theorem 2, we prove says the following. So how are the central charge? So we have related the central charge, which is a generating function of GLSM invariance, to the hemisphere partition function. So basically, this says if if you take you take a brane which and you take the central, you take the hemisphere partition function on chamber C plus, and you analytic continue it, you get the central charge. You get the hemisphere partition function of the image under this great restraint rule, which induce equivalence on matrix the category of matrix factorization, or the T-equivariant coherent sheaf, or the category of coherent sheaves. And then this gives the symplectic transformation in the zeta wall crossing. Okay, yeah, so sorry, sorry about the technical, all the technical issues. Thank you, yeah, for your attention.